Probably one of the oldest and most frequently used examples of the utility of smart contracts is weather insurance, where a farmer automatically gets paid out a coverage if their field did not get enough rainfall in a certain period of time. Many years later, this use case is still closer to marketing fiction than to reality, and that's because it's primarily a very tough data science and engineering problem. Before you get to a smart contract, you'll need to figure out how to source weather data in a decentralized way, ensure that it's valid, and then process these large volumes of data efficiently without re-centralizing it. In this tutorial, we'll take a stab at this problem, using Kamu for verifiable processing of both off-chain IoT data and on-chain analytics. Let's start by cloning the repository linked in the description and CDing into it. We then install Kamu using online installer and run Kamu init to initialize the workspace. Before continuing, we'll also run Kamu system diagnose command to make sure that our environment is correctly configured. We'll model our data on per device level, so let's go to the datasets directory and add our first dataset, weather station 1. Similarly to Kubernetes, in Kamu we define all data infrastructure as code with these YAML files. So this file declares a root dataset with a push source, allowing us to easily write data into it. It will accept NDJSON format as input, containing latitude, longitude, and accumulated precipitation. We run Kamu add command to create a dataset from this YAML file, and we can see that it's there now and empty. And we can add push data directly into it with Kamu ingest command. Of course, we'll need a lot more data than just one data point, so we will use ingest command again to add pre-generated data from a file. YAML files are just templates for how things should be created, so I can use the same file again to create a dataset for another device, weather station 2, and ingest generated data just like we did before. At this point, we can use Kamu's embedded SQL shell to explore the data, or use Kamu notebook command to launch integrated Jupyter notebook. Try running Jupyter yourself and executing generated data IPNB notebook to get a feel for it. In the notebook, we can use inline SQL to do most of the heavy processing on Kamu side and only get data we need for visualization into the kernel. Kamu is storing data in Open Data Fabric format. You may be familiar with Apache Iceberg or Delta used by enterprise data lakehouses, so ODF format is like a Web3 counterpart of them. Kamu log command shows that this format provides a very detailed history of how dataset evolved over time. Here you can see add data events that show addition of new records, set data schema that signifies schema changes, etc. ODF format specification explains that metadata is actually cryptographic ledger, where blocks reference one another by hashes, and likewise the Parquet files where data is actually stored, together forming this kind of hash graph or immutable Merkle DAG. First block of every dataset is a seed block that contains a DID or decentralized identifier. DIDs are essentially just cryptographic key pairs that serve two purposes. They give datasets global unique identity and let owner of the private key authorize operations through signing and encryption. DIDs and cryptographic ledgers are the foundation of personal data ownership. No matter how data is copied around the network, everyone will know exactly where it came from and who the rightful owner is, and make sure that the data is not tampered. ODF dataset, therefore, is a unit of ownership. So by separating our data on per device level, we're allowing different parties to decide whether they want to contribute data to our weather insurance system. Having one dataset per device is great for personal data ownership, but if our network grows to thousands of devices, working with this data will get very messy. We would like a convenience of one big dataset, but if we simply copy the data over, we will lose the ownership information that we worked so hard to establish. This is where derivative datasets come in. In the datasets directory, we have a weather station's global YAML file that defines one. You cannot write data to derivative datasets. Instead, you use them to express transformations on other datasets in the network. So here we declare both of our device datasets as inputs and specify an SQL transformation that uses Data Fusion Engine to perform union all operation and merge the data together while adding the device labels. When we add this dataset from a YAML file, it again will be created empty, so we will use Kamu pull command to make it perform the transformations. It executes almost instantly, and with list and tail commands, we can confirm that indeed the device data was successfully merged. Kamu log again shows all the details of the transformation that took place, but there's a better way to look at it. Using Kamu UI command, we can start the embedded web interface and switch to the History tab to inspect all the transactions. You can see that execute transform block records everything, the identities of each input, the block ranges that were considered, as well as the hashes of data that was produced as the output. On the Lineage tab, we see a visual representation of the pipeline we just created. A scale lineage exists in tools like dbt and Manta, but there's a very big difference. In enterprise tools, lineage is a bolt-on, a best effort hint to help you understand what the data is coming from. In Kamu, however, you cannot possibly transform data without creating detailed provenance and lineage. Derivative datasets in Kamu are a form of verifiable computing. They are deterministic and reproducible. You can send your derivative dataset to someone, and with Kamu verify command, they will be able to confirm that the data they see corresponds exactly to the SQL transformations declared in metadata. It's not possible for someone to modify, hide, or introduce some records without being exposed. Kamu provides a bunch of different ways to share datasets with other people. You can push them to S3 and other cloud storages, store them in decentralized file systems like IPFS. But for our application, we will need not only the storage, but also ability to run API queries on data. For this purpose, we have Kamu Node. Nodes are a compute component of ODF network. They share a lot of functionality with the CLI tool, but meant to run as servers as Kubernetes native applications. You can deploy one yourself by following our docs, but for our tutorial we will use Kamu Node that is a part of Kamu demo environment. Remember that by uploading data to a node in ODF network, you don't sacrifice neither ownership nor security. We first authenticate with a node using Kamu login command, and then using Kamu push, we can upload datasets to the node. Notice the special ODF over HTTPS protocol that heavily optimizes the transfer of data and metadata. We can now find our datasets in the node's web interface, which is the same UI you already used in the tool. In the Get Data menu, you will find a wide variety of protocols that the node provides for consuming the data, and we will use the simple JSON REST endpoint, which I'm demonstrating here. The response includes data, schema of the result, and also some state and hashes that will become important later. Now that we've taken care of the data supply, we can move on to building a smart contract. You can find the detailed instructions in the repo, but just as a general sequence of steps, we cd into the contract directory, use npm-ci to download the dependencies, and use Foundry's forge test command to compile and run the unit tests. Our contract consists of just one file, the insurance broker. The main purpose of the contract is to create these policy objects that include the address of the policy holder and the insurer, and store the ETH deposits from both to distribute when the policy is settled. Main functions include apply for coverage that holder uses to create the application and specify the desired policy parameters like precipitation threshold, bid for coverage, called by insurers to bid and provide the deposit. For simplicity, the contract just accepts the very first bid. And the settle function, called when policy needs to be finalized. This is where we'll need the data to decide in whose favor to settle the policy. To get the data, we'll be using an ODF-specific Oracle component. We receive the Oracle's address in the constructor argument and then wrap it with IODF client interface that only has one method, send request, and accepts the request object and a callback function that will run once the answer is ready. In the settle function, we initialize the request object and specify the dataset DID that will be queried, giving it an alias. Then comes an arbitrary complex SQL that we use to compute the total precipitation. Currently, we do a simple average across all devices, but we could also detect the outliers. We then execute the Oracle's sendRequest function and provide onResult method as a callback. The result object in our case will always contain just one record, the total precipitation, so we decode it as UN64 and compare it to the threshold stored in the policy to see whether we settle in holders or insurer's favor, and then transfer the ETH deposits accordingly. I already have the contract deployed on Ethereum Sepolia testnet, so we will run through one full interaction cycle together. Using npm run, I first run apply for coverage transaction under the holder's account to create the policy with parameters. Then I'm running bit for coverage as an ensure to enter the policy. After this, on either scan, we can see the event policy created. Then I'm using the settle transaction to initiate the settlement, and in either scan we can see a special event called send request emitted as part of it. This event is emitted by the Oracle to solicit responses to the SQL query. All the nodes can be configured with an optional Oracle provider component that will follow the logs of different blockchains, and once they see a request for dataset DID that they know about, they will all race to provide the results. So here in a different transaction, we can see that provide result event was emitted. This is our node submitting a result. And as part of the same transaction, our settlement callback is called. And we see that the policy was settled in favor of the holder. If you use Oracle networks like Chainlink, the interaction pattern is the same. But there is a significant difference under the hood, as ODF Oracle does not require a consensus mechanism. Oracle networks rely on complex consensus only because the APIs they call are non-reproducible. So multiple parties need to call the same API multiple times to agree on what response looks like. Otherwise, they may never see the same data again. This is slow and very computationally expensive. In ODF network, every query is fully reproducible and verifiable. This means that only a single node is needed to provide a response, which is cheap and efficient. Yet thanks to reproducibility, everyone else on the network can hold the node forever accountable for the validity of the response. They can verify and dispute it later. This makes ODF the first ever optimistic oracle. We have now taken care of the core business logic of our application, but if we launch it now, we'll have no observability into how the contract operates. Either scan is good for exploring individual transactions, but not very helpful for analytics. Projects like Dune and Flipside Crypto provide a SQL interface to query blockchain logs, but this would mean having a completely separate data solution for on-chain data. In our case, there is a huge value in having data from smart contracts side-by-side queryable with weather device data, as it would enable us to do all kinds of cool features like predicting the risk of claims based on weather trends and analyzing the areas where insurance is bought but needs more device coverage. Kamu can help to erase the boundary between off and on-chain data. Kamu comes with built-in ability to read data from blockchain nodes. In the datasets directory, let's open one of the broker contract datasets, and you will see that they all use this Ethereum log source, which can work with any EVM-compatible blockchain. Chain ID and node URL here specify which node to connect to. The filter section is like SQL where block that allows us to pre-filter logs using account address, block and transaction data, and topics to minimize our search space. And the optional signature allows to decode the binary log data directly into convenient fields and data types. Kamu will use all this information to create the most efficient RPC query and then continuously stream the logs from the blockchain node, which you can also pre-process with custom SQL. So you know the drill already. We add all the broker dataset files, and then using this %sign wildcard trick, we pull all the broker datasets at once. Data is ingested in a matter of seconds, and the tail command shows us a bunch of columns, including block and transaction info, as well as the decoded event columns with the holder and insurer data. We could use Jupyter to analyze data, but let's do something more interesting. I will push all these datasets to the same Kamu node we used before, and in the Get Data tab, let's take a note of the Flight SQL endpoint. Flight SQL is a successor of ODBC and JDBC protocols that many modern BI applications support. Here I have launched Apache Superset and set up a simple dashboard that calculates different metrics from our smart contract, using Kamu node as its data backend. This dashboard is a great way to have real-time awareness of how the contract is performing and what it's doing. We could go much further and use the same APIs to set up various monitoring, notification, and alert systems, including, for example, doing automated contract shutdown if some metrics indicate that our contract was exploited. Alright, so here we are. Let's take a step back to appreciate what we've built, because it's not a small feat. We created a fairly realistic data-intensive application with no central point of authority. Our source data layer promotes decentralized data publishing. We aggregate IoT data into one global dataset while preserving personal data ownership of device operators. We are processing these large volumes of data off-chain and get fully verifiable results in a smart contract, and then perform analytics across on and off-chain data without re-centralization. It's also important that we manage to build all of this using mostly just SQL and a handful of YAML files. We could test the entire data pipeline locally on our laptop without any accounts and signups, and only chose to outsource the storage and compute infrastructure to a third party for convenience without sacrificing ownership and security of data. This entire demo took me under a day to build. If I were using off-the-shelf indexers and oracles, I would need to stitch multiple different solutions together manually and also deploy and maintain my own big data warehouse to integrate all this data together, which would inevitably lead to centralization. Instead of building shared boundaries between on and off-chain data, Kamu is offering a unified data processing model, and we have many ideas in stock how to make the boundary between the two even less noticeable. So I hope you enjoyed this tutorial. Consider joining our Discord and checking out other online demos for more cool examples.